Hello, and welcome to Gravity, Motion, and Einstein. This is group Briley Mastis, Brendan O'Brien, and Russell Rounds.
Motion. Motion is described as speed, velocity, and acceleration. Speed is the rate at which an object moves. The equation for speed is distance over time, and its unit is meters per second. Velocity is speed and direction. An example of this would be 10 meters per second due east. To distinguish between speed and velocity, the following example can be given. 20 kilometers per hour due south is velocity, whereas 20 kilometers per hour just by itself is speed. Acceleration is any change in velocity, including a change of direction at a constant rate. Acceleration is speed over time. Its unit is meters per second squared. Examples of acceleration include turning, slowing down, and speeding up. Momentum and force. Momentum is mass times velocity. It depends on three factors: speed, direction, and mass. Net force changes momentum. This generally means a change in acceleration. Angular momentum is the rotational momentum of a spinning or orbiting object. Torque is a type of force that can change an object's angular momentum. Newton's laws of motion. Mass is the amount of matter in an object, and weight is the force that acts upon an object. Knowing these definitions can help us better understand Newton's laws. Newton's first law. Every object will continue to be in a state of rest or move at a constant speed in a straight line unless it is compelled to change by an outside force. The net force can change speed or direction. The key point here is that if there is no net force acting on the object, then the object will remain at a constant velocity. If that velocity is zero, then the object remains at rest. If an external force is applied, the velocity will change because of the force. Newton's second law. The change of motion of a body is proportional to and in the direction of the force acting on it. The greater the mass of the object being accelerated, the greater the amount of force needed to accelerate the object. The equation for force is mass times acceleration. Force is a push or pull and has both size and direction. When a force is applied to a body, the momentum changes in the direction the force is applied. Force is required to change either the speed and/or direction of a body. Newton's third law. For every action, there is an equal and opposite reaction. For every force, there is a reaction force that is equal in size but opposite in direction. When an object pushes another object, it gets pushed back in the opposite direction equally as hard.
Isaac Newton had this famous equation for figuring out mass and gravity in space. You can see it in the bold there with the key in the bottom left. I won't talk about it because you can easily read it. But he also talks about how gravity never hits zero. This is interesting because when you think about the sun and how far away Pluto is, how can the sun have so much gravitational pull on Pluto even though it's so far away? But it's true. It never hits zero. I mean, the pull on Pluto might not be as strong as it is on, let's say, Mercury, but it's still there. It's still making a pull on it to make it orbit the sun, which is very interesting, and Isaac Newton figured that out. When talking about center of mass and gravity, it's kind of a difficult concept to grasp, unless you can compare it to something here on Earth, like seesaws. If you think about center of mass as a seesaw on a playground, it's easy to think about. If you had two children equal weight, so on either side, they could both float in the air of the center of mass is in the middle. But if the bigger kid gets on the left side, the center of mass must change to more towards the left, as you can see in the middle diagram there. And lastly, on the last diagram there, it is possible. Say an adult sits on one side of the seesaw and a kid sits on the other. It is possible for that center of mass to be all the way, actually, basically where the adult is sitting, so they can both be floating in the air. It's kind of a weird concept, but this happens in space too. If you look at the sun and Jupiter, because the sun's mass is so much bigger than Jupiter's, the center of mass is all the way in the sun actually.
Einstein. Einstein opened humankind's eyes to the universe. He showed us what the universe has been like for the past couple of billions of years, and he made tons of breakthroughs throughout his life. Einstein's theory of relativity. Einstein extended Newton's theory on relativity, and he shocked the world in 1905. He determined that all laws of physics are the same for all non-accelerating objects. He published this theory in 2 steps: special theory of relativity in 1905 and general theory of relativity in 1915. Theory of relativity. It's made up of 3 rules. Every time you measure an object's speed, its momentum, or how it experiences time, it will always be measured in relation to something else. Second, the speed of light is the same no matter who measures it or how fast the person measuring it is going. 3. Nothing can travel faster than the speed of light. General relativity shows us just how extreme our universe is. It states that gravity pulling in one direction is equivalent to acceleration in another. It talks about how we perceive gravity, and explains the motions of planets and the history and expansion of our universe. Special relativity. Special relativity is a theory of structure of space-time. Laws are all the same in all internal frames, and the speed of light is the same for all observers.